Okay, Charles is in.
So hello everyone. Welcome to another career coaching webinar brought to you by Hamoye. As most of you already know, Hamoye is an edtech startup with a mission to prepare young professionals and college students for their choice careers in data. We do that via our internship programs, which simulates the conditions you will face while working in a real-world environment. Our internships will expose you to specially designed courses, industry-relevant capstone projects, and career coaching webinars with industry experts like what we are having right now. My name is Ayeni Rudolph, and I'm a data engineer at Hamoye AI Labs. I'm joining you from Akwa Ibom, Nigeria, and I'll be your host for this session. I'd like to welcome to the session everyone present, our incredible interns of the winter cohort 2022. A big ups to you for making it this far. I also like to give a big shout out to Hamoye fellows and the Hamoye team that have made this possible. We understand that sometimes data science journey can get a bit overwhelming, especially if you're just starting out. That's why we've brought one of our past interns from the Hamoye Data Science Internship 2021, Abdul Martin Omotosho, now working as a data scientist at Hamoye AI Labs. He's going to share his experience as an intern in the 2021 cohort and the internship's impact on his data science journey. Please sit back and listen. Hello, Abdul Martin.
Yeah, thank you very much for the brief introduction, Rudolph. So, hello everyone. I am Abdul Martin Omotosho, a student of Federal University of Agriculture, Abeokuta. I was formerly an intern at Hamoye during the last cohort and now a data scientist at Hamoye AI Labs. So today I will be sharing my experience as an intern at Hamoye with you guys. I'll be sharing some mistakes I made, challenges, and maybe recommend some few things at the end. I know you guys are currently at a stage in the internship where some of you are already demotivated and maybe some of you are planning to quit. So I hope this helps you guys to keep going. So before the internship, I was just a newbie to the data science field, and my only experience with analyzing and building of models was at the just concluded AI innovation program, which was organized in my school as at that time. And it was just a few weeks before the internship started. After the AI innovation program, I was added to the general AI Plus FUNAP group, where I came across the Hamoye internship. At first, I was reluctant to apply because I was having the feeling that I'm not qualified enough to do the internship. So later on, I registered for the internship since I had nothing to lose, even if I did not apply. So the internship started and we did the onboarding session during the first week. Then we started with stage A for the next 2 weeks. So one of the mistakes I made during the stage A was that I was overconfident. Like stage A was about introduction to Python. So when I saw the materials, I was like, I know Python already. I know pandas. So I just came through the materials quickly and jumped into the quiz. So it was the same way I jumped into the quiz that my score bounced me out back. I was humbled and I was very sure if I had gone through the material and made some research, I would have scored something much higher. So the leaderboard for the stage A came out and I was not even among the top 100 interns as at that time. I was not really discouraged with that, and I just hope to do better in stage B and not to make the same mistakes again. So moving on to stage D, I was a bit calm and I went through the materials provided very well. And anytime I came across a new subtopic there, I will just take note of it and make more research on it. So at the end of stage D, I had a perfect score and I was able to surface on the leaderboard. And that was really a boost for me. And one thing I also did wrong during this stage B was that I was not organizing my code very well. So immediately I saw that I had a perfect score during stage B. I just put the notebook directly into the GitHub without organizing my work, and I think that affected my notebook score. So I entered stage C with the excitement from stage B, and this stage was not really stressful for me. So I followed the instruction and did some research on my own, and also had a good score during this stage. And I moved onto the leaderboard. So moving on to stage D, this is the stage I considered like the most challenging for me. And this was the stage I considered quitting the internship for the very first time. Stage D was about deep learning. So the quiz, and it was divided into two parts, that is the part and the competition part. So the quiz part was not really hard for me, and I was able to do that within a short period of time. So the real issue started with the Kaggle competition. So for me to be able to access the data sets, my Kaggle account needed to be verified, which was not at that moment. So, and I was told that it will take like 2 weeks before Kaggle replied to my email and before I can get my account verified. And I have less than a week to finish the competition. So later, I found another way to get the data set, but I was faced with another issue of GPU. So if you are familiar with the Kaggle platform, you will notice that if your account is not verified, you will not be able to make use of their GPU on the platform. And this stage is about deep learning. So I need a GPU for me to train my model. So at that stage, I was thinking of dropping the internship, but later on, I asked some of my community members in school if any of them is with a verified Kaggle account. And thanks to God, I was able to get one at that time. So I started the competition and faced a lot of issues along the line. I was already familiar with using OpenCV to read in images, but this approach was not really working for me here because I'm working with a large image files, and that will require a lot of RAM. So after making some research, I later heard of the data gen method, which solves my issue. I was really stressed after this stage, but I thank God that I did not quit because at the end of this stage, I was now among the top 15 interns on the data science track. So moving on to the last stage of the internship, this was stage E. So during this stage, quitting was not even an option for me then because I've already done stage A, B, C, and D. So quitting at stage E will not really make sense for me. So I just have to keep pushing and not quitting. So this stage was also quite challenging because this happens to be the first time I'm hearing about time series analysis. But as usual, after finishing the course, I checked the reference material alongside some other materials to explore more about the topic before diving into the quiz. And at the end of the stage, I was among the top 10 interns on the data science track. And I was really proud of myself as at that time, and also proud of the program made so far. Because at the beginning of the internship, I was not even among the top 100 interns. And I finished the internship as one of the top 10 interns in the data science track. So, like I said before, some of you guys are at a stage in the internship where you are considering quitting or you are already demotivated. So, what I would just advise is that you should keep pushing, and also you should just take notes of some little information, because that's one of the things that really affected me at the early stage of the internship. Like I was overconfident and I ignored some useful information which would have helped me from the beginning. And
thank you very much, Abdul Martin, for sharing your tips with us. We really appreciate that insightful session. Thank you. I think a lot of interns can relate to feeling overconfident and being humbled. And thank you very much. I'm sure we picked up one or two things that we can use to help us keep pushing. So I'd like to get right into the topic for today. We have our guest with us, Mr. Charles Adetiloye. And for today's session, we have a rather interesting topic: enterprise machine learning operations in practice. So what is MLOps and why is it important? According to a recent study by New Vantage Partners of 70 leading enterprise companies, only 15% have deployed AI capabilities into widespread production. AI that is not deployed to generate value is only a very costly experiment. These experiments are complex technical accomplishments, but they don't translate into return on investment. MLOps allows companies to easily deploy, monitor, and update models in production, paving the way to AI with return on investment. So for this session, like I said earlier, we have an industry expert, Mr. Charles Adetiloye, and he's in a much better position to speak to us about MLOps. Mr. Charles has over 15 years worth of experience consulting and implementing large-scale data processing, AI and machine learning software platforms across different industry verticals. He has previously worked with Lightbend, Twitter, to name a few. He'll be sharing his thoughts and experience on how three tightly interwoven components of MLOps, machine learning, DevOps, and data engineering can be adopted for entrepreneurial activities. It's a pleasure to have you join us, sir. Okay, just before we hand over to Mr. Charles, please take note of the following. Feel free to use our chat boxes on Zoom and YouTube for comments, questions, and conversations around the topic. Rest assured that all questions will be attended to. A Google form will be opened right now, and that form is to get the attendance for all the interns that are present. The secret code is "We love code," all lowercase. Like I just said, a Google form will be opened right now, and that form is for attendance sake. So the secret code is "We love code." That form will be opened for only 10 minutes. After 10 minutes, you will not be able to access the form anymore. But also note that a second attendance form will be opened later on in the session, and the secret code will be announced once it's open. So at this point, I'm going to hand over to Mr. Charles Adetiloye, and I'll ask that you sit back, relax, and get ready to learn a lot from this session.
Thank you very much for the introduction, and good morning, good day, and good evening to everyone, wherever you are. So today we're going to be talking about a very interesting topic, which I think a lot of you are very excited about as well. It's something we do all the time, and we're just trying to introduce you to the best practices in MLOps and things like that. So to get started, I'm going to share my screen. If you will give me 1 second, and we can get going. Can everyone see my screen?
Yes, we can see your screen.
All right, cool. I'm going to flip it all the way back. Okay, so today we're going to be talking about MLOps in practice, what you do professionally as an MLOps engineer, and things like that. So a little bit about us for those of you who are getting to know about MavenCode, if you're new to this. We're like an artificial intelligence solutions company based out of Texas. We do training, product development, and consulting, with specialization in provisioning ML pipelines on-prem and in the cloud for our customers. We deploy and develop machine learning platforms on-prem and in the cloud. We do enterprise feature start deployment and development for customers trying to build models. We do things around model management, model governance, and streaming data analytics, edge IoT, and model deployment. So some of the industry verticals we've worked in and we serve include retail, insurance industry, automotive, healthcare, agriculture, energy, travel, telco, and the agriculture industry. So there's a quick video, but I'm going to skip it just to like move fast enough, and because so that we can move fast enough. So let's just go to the agenda for today. So we're going to go through the overview of MLOps, various MLOps roles, the MLOps landscape. We'll discuss the use cases around MLOps. We'll leave some time for questions and answers so that we can address some of the questions that may pop up and things like that as we go. So overview of MLOps. So as far back as 2014, a group of Google researchers published a paper on this subject. There's a huge technical depth whenever you're trying to deploy a model and develop a model and put it into production at scale. Nobody better understands that than Google. Because basically Google is an AI company. So one of the things I found out was like, it's easy for anybody to just build your models with Jupyter Notebook, do your analysis and everything that you're doing. But how do you get these things to scale in production? Whenever you're trying to serve, let's say 1,000 people are trying to consume your model every second, 100,000 people are trying to consume your model every second. How do you get the model to scale without buckling, without failing? And things like that. So that's where MLOps come into play, where how do you release your model? How do you tag and label how do you prepare your data to train your model continuously? Because building model is not something that is static like traditional programming. You basically need to retrain your model over and over, time after time, to make sure things are showing up the right way. So just to give it paint a picture of the way things are right now. So you can see the trend in the last few years and few months. A lot of all these companies are realizing that, okay, it's not just about hiring data scientists or hiring data engineers. We need to be able to have a practice around building models and serving models at scale. So which is where MLOps comes into play and things like that. So just to paint a simple picture of this, MLOps is not easy. It's a complex task. It's kind of like launching a rocket. Launching a rocket is easy. Anybody can launch a rocket even from your backyard. But the question is like, can you get it successfully into the space? Which is where the hard work is. You need to map your trajectory, make sure the rocket gets into orbit and things like that. So it's a hard task, just not to sugarcoat it and paint the real picture of things. So just to validate that, you see a lot of, there's a popular tweet. If you go look at this, Andrew, I think she used to work for IBM. It's like, it took me 3 weeks to develop a model, but it's been 11 months and it's still not deployed. So you train your model, your algorithm work, everything in your model works, but you can still get this model into production. So that's a huge challenge in a lot of organizations. People try, but they still fail. So the question is like, it's beautiful when you write all those cool things and you have your Jupyter Notebook running, you basically train your model, the predictions are right, but how can I get it out in front of people so that I can inference at scale, I can make predictions and I can make this model productive enough to affect people's life and augment all the things that they do by themselves right now and make them a lot more efficient. So on the average, 40% of companies said it takes 1 month to deploy ML models into production. That's true. We see that a lot as well. So what's machine learning operations or MLOps in short? It basically helps simplify the processes involved in deployment of machine learning models between operations team and machine learning researchers or data scientists. So if you look at a big organization, they have a bunch of data scientists building the algorithms. You have traditional software engineers. You have DevOps guys who are like used to like building continuous integration and deployment environment for your software. But you need to have everybody work together and have a changing perspective in terms of how things should work now that you're doing MLOps. MLOps is not like your traditional DevOps in that with DevOps, you're only doing one thing. You're compiling code and you're making sure that that code compiles all the time and you're not introducing any regression. But with MLOps, you're dealing with more variables. You're dealing with like your input data for training. You're dealing with the algorithm that you're using and you have an output artifact, which is a model. and you want to make sure that the model is accurate. If it's not accurate, you have to retrain it and things like that. So that introduces more complexity because you have more inputs into your MLOps process. So we can say with MLOps, the goal is to standardize and streamline the machine learning lifecycle management. So from the start of picking your data, selecting your data, training the data, training your model with the data, making sure you have the right input, your feature engineering, and producing the output model, the entire life cycle, we want to be able to automate it. So that's the whole goal of MLOps. And it's a critical component of any successful machine learning project in the enterprise. So if you want to build your own company or you want to create a startup and you're doing AI things, the goal is to have a very efficient MLOps process that can get you from point A to point B or C, and you can repeat the cycle over and over. So that's the goal of, that's one of the goals of MLOps. And organizations generate long-term values and mitigates risk associated with machine learning projects if you have a good MLOps process. So you're basically creating a best practice so that, AI projects are very expensive. People are new to this space. So there's a high risk involved. The likelihood of the project not succeeding is more than the likelihood of it succeeding. So one of the things you want to do is to mitigate any risk associated with any project you're doing and making sure that things come out right and things like that. So as an organization where you have a bunch of developers, data scientists, machine learning engineers, and stuff like that, you want to make sure you mitigate all this risk associated with ML by having a good MLOps practice in place in your organization. So just to paint a picture in any given organization, and as you guys go into the industry, particularly those who will be working extensively in AI companies, one of the things you find out as in the enterprise, in any big organization is like one, you have data scientists working on stuff, but you can't reproduce it. So you work on your laptop, the old model, the inferencing works fine, but you can't really reproduce whatever you're doing easily. So that's one of the challenges in place. It's not easy to reproduce the process of ML training, the deployment, and all the iterative runs. So that's one of the challenges. And the reason for that is probably because you're working on your local and you don't have a process of getting your model into production. The other big problem is reusability. One of the problems that were solved early on in programming was introducing the concept of object-oriented programming and APIs so that you can reuse components and stuff like that. But ML pipelines and ML process are not very mature to a point where they're reusable right now. That a lot of efforts in that direction, things like components in Kubeflow pipeline that allows you to like create components that you can reuse as part of your ML pipeline, ML workflow. So, but the whole idea of having a reusable pipeline is very important in enterprise ML. The other thing is manageability. You're training a bunch of models and you want to select the best performing model because you don't want to introduce any false positives or anything that is not accurate as a result of your prediction. So having a place where you can version control your model output so that you can know like, okay, when we made this prediction 6 months ago, we used this model and this was the results. When we made this prediction 6 years ago, this was the model we used and this was the results. So managing the model and not just building it and training it with every time you basically train them, every time we train the pipeline, I think is very important. So manageability of your model output artifacts. And it's very important as well for audit trails. So if you're doing prediction in if you're building models for mission critical application, you want to be able to track everything just in case you need to do audit trail of what happened, what the model predicted, what's the ground truth, so you want to verify that what you did was right. So the manageability of the whole process, keeping track of all the model artifacts that you produced, I think is very, very, very important as well. And finally, the need for automation. So there's still a challenge in this place where people think traditionally the way they do the CI/CD deployment, so which is a lot more different from the traditional MLOps process. So just to paint a quick overview of what happens in a big organization doing ML, not necessarily big, but in organizations trying to approach things with trying to build ML. So the people generally think that machine learning is very simple, like you just write your Jupyter notebook and stuff like that. I think this is a common slide that we've seen, but the whole process is very huge. You have different components coming together to make up a successful model that you deploy into production that becomes something like Uber, Facebook, or Google. They have a lot of all this model process that they build, and you have to like do a lot of all these things. You have to do data verification to make sure your data is all right. You validate the data. You make sure you configure your resource to be able to like pick up the right data sets. You do feature extraction and feature engineering. On this side, you need to worry about the GPUs, the resource that you need to train the model, the serving infrastructure for serving the model, monitoring the results to make sure there's no drift, the results are accurate enough, and there's no implicit bias or any bias in the prediction results and stuff like that. Then while you're doing that, you still need to expose an interface for your business analyst or domain expert to analyze the output of the model and see if the results are actually accurate or not. So with what we've seen in the previous slide, one thing that you see a lot in a big organization, if you want to look at things from roles and responsibility perspective, is you have different roles in any organization doing ML. Roughly, you see a lot of things like this, where let me admit this people. You have subject matter expert that understand the domain. Whatever you're trying to build a model for, somebody probably worked on it manually years ago, and you're just trying to automate it and make it scale. So there are people called the subject matter expert that have been doing this for years. You never underestimate their knowledge because they understand everything from end to end. Whatever you're trying to do, they understand the domain. They provide business questions for framing ML models. They define the key performance index to be achieved so that if the model can do this, then they can trust it. And they help you evaluate the results and things like that. So they're called the subject matter expert. They come in with like all this repository of knowledge that you don't want to discount. Then data scientists typically work with these people to like understand all those things they've done. So you identify the features that you need to build a model, and you deliver an operationalizable model for production deployment. So that means you basically understand what they said. You prepare the data based on the inputs you get from the SMEs, and you take that input, you use it to like deliver models that you can basically that can be productionalized. So that means your code is well written, everything is good. You've trained and tested your model locally. And data engineers basically work with data scientists to make sure you have access to data for the project. You have they optimize the process of pulling the data around, because in any big organization, they have all this data in different departments and they're all siloed across. So the data engineer basically works to like make sure you have access to all this data and stuff like that. So then you have the ML engineers that basically integrate models into applications. So when you see all these intelligent applications, you basically book an Uber, you make a request on Uber, they connect you with a driver, and everybody appears and stuff like that. So the ML engineers basically understand how you integrate all these things, how you do the inferencing, how you tie the results to other applications downstream in the organization, making sure you promote the next available model into production and things like that. Then you have the traditional DevOps engineer who now needs to like understand how to like put all this system together, basically building pipelines for continuously training model. Whenever you have a new data, you basically trigger the process to retrain the model, and that model gets deployed, and you do like quick A/B testing or whatever you need to do. Then once you have that result, once you have a result and you can stage your model for inferencing, you have the model risk managers and auditors that go in and analyze the business goal and the model outcome. So there should be minimal, extremely minimal divergence between these two. If the model goal is to have the model predict X and it's predicting Y, then there's a huge problem. So if it's predicting X or almost X, then I think there's a reason to be confident about your model and your process you've put in place. And it might not make sense if you're doing something that's not mission critical, but imagine you're working on a self-driving car and the self-driving car is not able to identify pedestrian on the road. The model in the self-driving car is not able to identify the pedestrian on the road. That's a big problem. So before you put this model into production, before you put it in the field, you have the model risk managers and auditors coming into play, checking the model to make sure things are okay and everything is all right. And you have the ML architect who is responsible for the overall picture of things, how things are laid out, how the system connects to each other, and stuff like that. So just to show this in a little bit more interesting way based on the roles and responsibility. So this is a typical workflow whenever you're starting any ML project in a big organization. You have a subject matter expert asking business questions like, okay, we want this model to recommend stuff to these users based on these variables and stuff like that. Let's assume you're running an e-commerce website and you're selling something. Basically, the subject matter expert understands and knows if people buy these items, the next thing they're going to buy is this. So how can I get people who are buying item 1 to also buy item 2, 3, and 4, and 5? So the whole idea of this SME is the role of SME in any project is that they understand the business, they'll ask valid questions, and those questions are what you use to like capture the data that you need to train the model. So based on what the SME says, you have the data engineers working hand in hand with data scientists, data engineer looking around to see where we can acquire the data to train the model. You do data preparation, which is, okay, data scientist says like, okay, I need this data in this form and in this way. The role of the data engineer is to basically acquire all this data in the right format and basically prepare the data. You do something called feature engineering, which we're going to talk about later on, which is like all about selecting what you need to train the model. And you build a model, you run several experiments. It's not like your first model is always the right one, like most of you will know. Maybe we've done this before. And you have data scientists basically training model, running several experiments, comparing the results, seeing if the result is okay. If it's not, then you iteratively go through the process again. At some point, you check in with the subject matter experts and run what you're doing by them to make sure things are okay. So this is kind of like the development life cycle, the process of like getting your model in play, getting things ready and getting it ready to go. Then after that, you have the preparation for production. Once the subject matter experts and everyone agrees that, okay, the model is accurate, the result is good enough, you need to prepare for production. That means you need to have a pipeline where you have a runtime environment. The risk evaluation is in play so that if there's any risk in that model, or if it's going to cause any problem, you can stop it and go back and retrain it or recreate a model again. So you do the risk evaluation. You ask, there's Q&A. So for this, QA basically is testing to make sure the results are okay in a large scale, because when you're developing, you're probably looking at the inference result from your own model predictions alone. But once you start doing QA, you expose the results to more people, and they can test and see if the results are accurate across a larger sample of the data sets. So then the next thing, once everything is okay, is like you start thinking about how you can get this into production. So you think about things like containerization, continuous integration, scalability. So basically, you're not just thinking about running this alone with just maybe a few users. You're thinking about like, okay, if it's a big model, if it's a big project, you're talking about maybe thousands of requests per second. So how do you scale out this process to make sure it's efficient enough for people trying to like access the model and things like that? Then you want to containerize the model as well. Things like Docker and Kubernetes if you're running on Kubernetes, and you want to have a continuous repeatable process so that every time you train a model, you can easily get it deployed and stuff like that. Then once you deploy the model, the next thing you worry about is feedback. So it's not like you deploy a model and that's it. That's the end of the work. No, your work starts again from the deployment where you monitor the model, you do logging, you log all the requests coming in just to make sure you have a log that you can analyze. If there's something that is wacky about the prediction, you want to be able to alert the organization or people monitoring the model, like the DevOps guy or the ML engineers, to tell them that something is going wrong. Then you want to track the model for drift, because over time, your model prediction is going to drift from what the model predicted originally, because you trained on the samples data on a particular type of data set. So as you start getting data that like not part of the original sample, your result may drift. So you need to track that drift and feed it back into the pipeline to retrain the model. And you evaluate the drift. So if the drift is not large enough to trigger retraining, then maybe you can still live with it. But once you see a huge divergence between the expected results and the ground truth, then the ground truth and the prediction, then you need to go back and retrain your model and things like that. So the monitoring and feedback loop is very important. So it goes back and you basically acquire more data to retrain the model and get a better performing model out there. So that's it about the roles and responsibilities. So let's just go into the MLOps landscape. So a typical machine learning pipeline looks like this, where you have data source. It could be streaming data like Uber or IoT, or it could be batched data that you just acquire from your database, or a batch dump of files that you're trying to process. And you basically do something called feature engineering. So the data is not yet in the purest form. You need to get the data in the form that you can use to train your model. So most of the time, there's some fields that you don't need. There's some fields that are in the wrong format. And there's some fields that you need to like change. In some cases, you're dealing with like, for instance, if you're in the healthcare space where you have patient data, you might need to anonymize the patient's name and things like that. You mask out the patient name. I mean, there are a lot of things that you do, which is part of the feature engineering process. So you have the data extraction, you extract your data, you process your data, you analyze it, and you push it out there. Then the next thing, once you have done the feature engineering, which you have all the features that you need to train the model, so you're not bringing in the entire raw data set that you acquired. You basically have all the input that fits into the model. Then you can start doing your model training and evaluation of the model to make sure it's predicting the right results. Then once you've done that, you're probably going to train several models because it's not really the first model that you train that will give you the best results. So you probably go through multiple iterations. You change your input hyperparameter. You train and retrain and retrain and retrain the model. So you create different versions. Then you can now select the best performing version of your model. And once you do that, the next thing is like you can now deploy your model for inferencing. So you can deploy your model for inferencing, where that's called the model serving. And you monitor the model, you see the predicted results, you're looking at the logs and making sure everything is okay. Then you can now integrate this with your app. So that's how you consume the model on your mobile app or your web application or wherever the app is, the model is deployed. It could be like your edge IoT devices on the field and things like that. So typical ML engineer or data scientist workflow looks like this. Once you're building, you're trying to train a model, just to zone in on what will interest you guys. So most of you guys are typically your ML engineers, data scientist, or data engineer. You're looking to become one of that if you're not yet. So you have the storage where you keep all the data that you need for training that you're pulling. The storage could be from anywhere, PubSub, MessageQ, Kafka, database, story bucket, and things like that. So you pre-process the data. So you're gonna have a pipeline that brings in all this data, process it, and you select the features that you need to train the model. So you have a storage part. So all these things live in the storage. where you have a pipeline that the job of a pipeline is to just do this every day for you. So as you get more data, you're basically transforming the data, processing the data, creating all these features and everything that you need. Then once you process the data and you have all these things that you need, you write it back to all the story bucket. And in the story bucket, you create the output that you can use to feed the model. So this is where you basically train the training process. So you have the data scientist or data engineer pull in the feature engineered input data sets, and you can now train your model. So there are different platforms that you can use for training your model. Google has a GCP Vertex that contains Jupyter Notebook and allows you to create a pipeline. AWS has SageMaker that allows you to train with AWS SageMaker. Azure has Azure ML and Azure. And if you're doing on-prem or you want to do things your own way, or you have a Kubeflow project that basically helps you abstract the process. And you can basically have a platform that allows you to train your model from end to end. So they're different, all these things achieve the same thing at the end of the day, but they have different opinionated ways of doing this. So Google has their own way of doing things, AWS has it, Azure has it, Kubeflow too has a way of doing things. So depending on what you're doing, you can determine what platform. Your organization may be like a multi-cloud or they may have a multi-cloud strategy, so they have all these cloud providers, and you're working across all these things and stuff like that. So this is a typical landscape in terms of what the ML engineer or data scientist would do from day to day, running on all these cloud platforms and building and producing models from them. So things get a little bit more complex as you scale the organization or as more people join. So like if your organization is running on Google Cloud, AWS, Azure, or they have on-prem resource and they have different teams doing their own things, it becomes a lot more complex to get things done. So because you have a storage, data sourcing, pre-processing, feature engineering, the storage part, you have the compute part, where the people are basically pulling all this data and trying to do things their own way. We have a team working on Google Cloud. You have a team working on AWS SageMaker, or another team working on Azure ML, or another team working with Kubeflow. So it becomes a lot more complex, and most of the time, this team are pulling the same data in different ways. And things get a little bit more complex as you try to scale your team and things like that. So since the goal is to create a best practice in the organization, we need to have a way of abstracting all these things to make it easy for everyone in the organization to collaboratively work together and create a seamless working environment in terms of how you access the data, how you share the data, and stuff like that. So to simplify that complex diagram that you just saw, so we can think about the data processing part, which most of the time involved like pulling your data and storing the data for model training as a storage requirement. And you can think about the model training part where you basically do your model training, scoring, and evaluation as a compute resource requirement, where for this part, you need a lot of CPU. For this part, you need a lot of storage, like having going, even though you still do some computes while you do your data transformation and stuff like that. But for the most part, you're paying a lot more for like storage in most cases. In this stage of in this stage of the process, you need to have enough storage to like bring in your data, pre-process it and make it ready for consumption and stuff like that. So to make things easy, one of the things we look at, because we're heavily invested in cloud native deployments at MavenCode, we look at abstraction of all this process so that we can build a reproducible best practice that simplifies the process. So the story part, we kind of like think about it as creating a feature store or providing a feature store environment where I can constantly train and produce output that can be kept in the feature store, and from the feature store, the data scientist can just log in and consume it. So every day I acquire data, I have a process that transforms the data, identify all the features I need, puts it in a table, if you want to think about it that way, and makes it available for the data scientist. So, and it could be, the table could contain many fields, and different data scientists will need different fields, but basically simplify the work of the data scientist because they don't have to worry about the underlying uh, process of sourcing for this data uh, from different locations. The data is already available for them every day. It's pre-processed. It's available so they can just query and access the schema and pull the data that they need. And on the other side of the compute, one of the things we've invested a lot in on at MavenCode is Kubernetes. Basically creating containers that can run on Kubernetes. So that way I have an elastic compute resource that can scale and I can easily containerize the model, put it on Kubernetes. So as each data scientist are training, they can basically train on the Kubernetes resource and it's cloud agnostic. So if you ever decide to shift between a particular cloud operator, and from a particular cloud provider to another, if you're running on Kubernetes, it's just you being able to like redeploy in that new environment. So it creates a better abstraction and a way for you to shift and lift your resource so that you're not tightly coupled to a particular infrastructure and things like that. So again, for the feature store, there are different solutions out there, open source projects that you might want to look at. There's OpsWorks feature store. There's one called Feast. There's Databricks has a feature store as well that they provide for their customers. So you might want to look into that. So the goal of the feature store is for you to source all the data you need, put them in one point, so that the data scientist is not spending valuable time looking around for all this data. You have a global schema and people in the organization can access that schema for the data set they need. And if it's not there, then you can create a new version of the schema and extend the feature store to support this kind of data set that people are looking for. So, and the other part is leveraging Kubeflow, which we'll talk about a little bit more, to run your machine learning pipelines and stuff like that. So this basically simplifies the whole process of training, running, sourcing for data, training and stuff like that. If you're running a big organization and you have a big team working hand in hand and stuff like that, it basically simplifies the whole process for them. So we'll talk briefly about feature store, just to like help you guys understand what a feature store is. So a feature store is a measurable, observable attribute that is part of input to a machine learning model. Think about it this way: you're training a model, most of you are grabbing the data from Kaggle, and for you to like feed the data to your model, you do some analysis, you determine what input feature vectors or features you need to train your model. The ones that you're not going to use, you drop it off and stuff like that. So basically, imagine you're not getting that data from Kaggle and you're just in a company where there are different databases, different sources of the data. So you need to be able to like combine and provide data to your model. So one of the problems that feature store tries to solve is to prepare all this data for you as a data scientist. So you can just connect to the feature store, request for the feature vectors you need, and you use to train your model, and you produce a model output. So it basically simplifies the whole process of training model and training model for the data scientists and things like that. So your feature vector could be anything from you derive from your raw data store, a streaming data store, or aggregates of inputs. You could create windows. So let's say you're ingesting data continuously to a message queue. So you can create windows where every minute you compute the features you need, you put it in the feature store, or it could be hourly, or it could be daily, or weekly, depending on the resolution you want. So you can create an aggregate window for your feature store and all the data you need. So once you've created your feature vector, you feed it into the model for training, and you produce your output model. And features changes over time. So that's one advantage of having a feature store is like the input attributes you use to train your model is going to change over the years. From like say 10 years ago up until now, there's been a lot of different things that have happened to your data set. So all these features keep changing. So, but one of the advantages of feature store is like it allows you to do time travel. So you can go back in time, like, okay, we're doing a model predicted that we're gonna have this, or we had this forecast 6 months ago from our model. You can go back and basically do a time travel and select the data set up until like 6 months ago and use it to train and see if the prediction or the forecast is measuring with what you're having right now. So the cool thing about the feature store is like it gives you that time capability so that you can view data as a continuous stream that flows over time. And you can easily go back in time or travel forward in time if you want to basically simulate some future data sets and stuff like that. So, but it basically simplifies the whole process so that you don't worry about like a lot of all these things. It organizes your data for you, and a lot of companies are gravitating towards having feature store in place for their model training and stuff like that. So that's one of the big advantages of abstracting everything you do in a big organization into feature store that you can use to train your model. So feature stores and MLOps makes it easy to operationalize ML workload. Most importantly, the data management and the storage for model training. Features can be easily shared among teams. So like I said earlier, there's no sense in pulling the same thing and computing the same data over and over across multiple teams, even though they all need the same data. So you can abstract all those things as features. And these features can be shared by teams. So each data scientist just goes in, select the features in it, and they can use the train and model. So that's one advantage of it. And we can get to version data sets and track changes easily. So one of the things you want to do whenever you're doing model training is like, you want to know the data you use to like train your model and the output model that was produced, just in case you want to do an audit. If something goes wrong, you want to be able to like trace everything all the way from the input data sets to the model output that you produce to the pipeline that train the model and all those good stuff and the version of the code that you compiled and stuff like that. So the goal, the feature store basically helps you on the data management side to keep track of your data sets over time. As things changes, you can see the version, the dates, the timestamp on the data and stuff like that. And it creates a consistency. There's a consistency in feature input attributes between model training and model serving. That's one thing I didn't deep dive on, but if let's say feature store allows you to abstract what you basically put into the model. So like you create a set of input vectors, you train and you get a result. But whenever you're trying to serve the model, let's say you have a user ID with a username and the user, let's say age as part of your feature store, but you're not using the username and the age for your training. But whenever you're trying to serve the model, you don't want to like present the user ID to the user. You want to transform it back to the name and the age. So with the feature store, you can do that transformation easily because it allows you to basically, it creates a consistency between the input vector that went into the model and the inferencing that you produce on the output, so that if you need to like load a complete view of the data sets of the feature vector role that you used in training the model, if you need to load it on the other side, you can easily call it and load it with, through your serving infrastructure and things like that. So getting data into the feature store, it basically involves having a pipeline. So you can create a pipeline that, in this case, we have a Kafka reader that basically connects to a Kafka message queue. We have a component that basically connects to the data stream, pulls the data, does some validation, does some pre-processing, and we have a feature store writer that basically allows us to like write the feature that we have into an UDI table. So UDI basically is like a Delta Lake the data store that we use. It basically allows you to like capture. You can use it as a feature store because you can create you can basically add incremental changes that happens to your training or data set to your data sets to the UDI data store. So we have the UDI writer that basically allows us to like save data to the UDI table in a very incremental way, so that over time you can see the timestamp, you can know when you added the data and stuff like that. So we use that as a feature store for some projects. There are other projects as well, like the Delta IO, which allows you to do the same thing from Databricks. So the whole idea of the feature store basically is allowing you to compute and compose your data for model training and things like that. So this is a simplified version of a schema. In some cases, you might have multiple data sources that you're combining together, Kafka, database, or message queue, or file system. So you put everything in place. You create a schema representation of the data sets. and you basically compute the data you need to put in the data sets and write it to the table. So let's look at Kubeflow a little bit real quick for MLOps. So Kubeflow basically allows us to do most of the compute that we do on the other side. Like I said earlier, the goal of anything that we do in the enterprise is for us to be able to like reproduce the process. We want to build a reusable components. We want to make sure it's manageable, and we want to automate it. So we achieved a lot of this leveraging Kubeflow, which is an open source project, a lot at MavenCode. So the whole idea of Kubeflow is to solve some of the things we mentioned earlier as challenges. You want to be able to like compose the building blocks of your pipeline. So the composability is a big part of it. And you get that on top of Kubernetes easily because you can create containerized infrastructure that you chain up together. So you can have different containers connected together, and you can easily replace. So you can think about it as a Lego block. The composability aspect is there. You have the portability part where I can shift between on-prem and in the cloud or my local, and the scalability part. So you don't have to worry about how do I scale this? What if all of a sudden my model is the request to my model just goes up by 10x or 100x? You have the underlying infrastructure and to support this kind of scaling, and that's one of the advantages of Kubernetes and with Kubeflow on top of it. So Kubeflow basically is a machine learning toolkit for Kubernetes. It lives on Kubernetes. A platform to productionalize ML models, making it simple and scalable and reliable. There's a collection of cloud native tools for all stages of model development lifecycle. So every stage you go through in the model development lifecycle, there are sets of tools for doing that, and it sits on top of Kubernetes. And it allows you to build integrated end-to-end pipeline, which connect all the stages together, and for your model training and the entire model deployment lifecycle. So simply put, Kubeflow simplifies the model development lifecycle. So you can look at it, Kubeflow general layout as something like this. You have different tools on top of it. You have Jupyter Notebook where you can write your code. You have PyTorch framework, TensorFlow framework, MXNet, Scikit-learn, and XGBoost. So once you install Kubeflow on your local, or if you have it installed on the cloud or on-prem, you get that right out of the box. Then you have other applications running on it called operators. Operators basically manages the lifecycle of the container from the point of start to finish on Kubernetes. So there's a concept of operators that manages all these things. So you have different things, applications running on Kubeflow. So you have the Jupyter Notebook available to you, like I said earlier. You have different model training operators like the MXNet, NPI, PyTorch, TFJob for TensorFlow job, XGBoost. And you have the pipelines for composing your pipelines. There's a UI and there's a serving infrastructure, and there's a TensorFlow for batch prediction as well. They have other optional things that comes, but you don't really interact with them right out of the box. These are like contributed for the most part, like the serving, the TensorFlow serving, Solidon for serving. So those are like Knative serving. Those are like infrastructure for serving your model, so you can go with different options. And they have Prometheus for like monitoring the logs and seeing that everything is okay. They have Argo for workflow. They have Istio for controlling the traffic and securing the perimeter of the cluster so that you only get authorized ingress requests to the Kubernetes cluster. If it's not authorized, it's not going to be able to get in. So once you install it, and I will encourage you guys to go check out the project. It's open source, you can grab it. So it's not like you need to pay for it. So it's easier. So once you install Kubeflow, you have a dashboard like this that contains most of the things you're trying to do as an ML engineer, data scientist, data engineer. So you have all these things that you basically can click on and do your work. So in a big enterprise, this is how the landscape looks. Where you have a Kubernetes cluster, you have the underlying Kubernetes nodes. Those are like a compute, your servers, each one running Kubernetes. And in case if you're doing anything that involves like image processing, you have GPU nodes as well. So All these resources scalable. So what that means is like as you have more work or more training going on, it's very elastic. It's going to expand and allow you to do your compute. And once you're done with your compute, it shrinks back and stuff like that. So the whole idea is to have this scalable infrastructure where if people are not using it, you can basically reduce the footprint. And during the day when people are doing a lot of training and there's a lot of work going on, you expand the footprint and people can do a lot more. So this is Kubeflow, managing, providing the infrastructure for each data scientist or data engineer or ML engineer, if whoever is working on it. And you can basically have your own section where you do your training. Once you do your training, you schedule your job. It runs on the cluster, and the cluster can scale up or scale down depending on the needs. And if you want to collaborate, you have a space where you can collaborate as well. That means you, whatever notebook you're working on, you can share with like other engineers and they can see what you're doing. So basically, each environment is secured with Istio. So you can control the traffic based on the role-based access authorization ABAC. So you have an identity and you can tie it to the authentication framework that the organization is using. So they're using, you have DEX that connects to different OAuth provider. So that means if you're trying to sign in, it will validate your authenticate you. And you can tie it into like things like GitHub or Gmail or whatever provider, OAuth provider the organization uses. So you can tie it into that. So it forces you to authenticate and notarize correctly and stuff like that. So all these things, this is a big picture of how things look in an enterprise and doing AI and ML where you have a lot of teams collaborating and doing things together. So I'm going to skip this slide. It's specific to Vertex AI, which is a product that Google works on. So let's walk through a scenario where it's an airline customer prediction. You got this data from Kaggle. So we just want to go through the scenario. So of how things work in a big project. So, but this data set is from Kaggle, it's not from any organization, just a full disclaimer. So the data is from the airline organization whose actual name is not given for various reasons. Therefore, the airline is given a pseudonym of Investco Airlines. So you have different data sets. So let's say you're the manager of this organization. You're trying to predict how to increase customer satisfaction. So you have a subject matter expert and the data scientists coming together. They'll brainstorm on what they need to do and how they need to do it. So the problem statements from the subject matter expert will be like, okay, customer satisfaction is a priority in the airline industry. They want to know they're unhappy or there's a good customer, and so that they can easily address their problem and things like that. So satisfaction is really solely based about the flight itself, but the experience from booking to landing. So how can they improve their process? All the process involved from the time you book your flights to the time you enter the plane to the time you land, so that the next time if you're trying to book an airline, you don't go to their competition, you just come back to them and stuff like that. So that could be a problem statement that you're trying to solve. So the next thing you do is to you do your data analysis. Basically analyzing the data that shows the satisfaction and the dissatisfied customer. You go out, you put a survey out there, people fill the survey and the results. You see the number of satisfied and unsatisfied customer. You do further analysis, you break it down by gender, male and female. You analyze the travel type, like what travel types are people more satisfied or less satisfied and things like that. Is it business travel or personal travel? You can see the difference. Then the customers in business class seats were more satisfied based on the way they were treated and stuff like that. So these are like all the initial exploratory data analysis that you do. You do it maps showing the feature correlation so that you can identify the features that basically are very important for model training. So that if you want to build a model, that model can either tell you what you need to improve on for each customer type, depending on their seat type and stuff like that. So the data scientists still work with the subject matter expert in this case. Then once you basically identify all those things from your initial analysis, the data scientists will start working with the data engineers for the feature engineering. Things like removing outliers, dropping data that are not valid, combining columns with little or no correlation with a variable. And in some cases, you want to convert categorical features to numbers. So the outlier remover with block spot plots before and after. So basically, the data scientist work with the data engineer to compare the results and see how things look. And once you've done that, the next thing now is to create your feature engineering data pipeline that basically allows you to load your data, process the data, and create the output that you want, that you need to actually use to train the model. So the data engineer basically creates this pipeline, gets the data, reads it from the source, run a lot of statistics on it, it basically codifies whatever the data scientists have in the Python notebook. You build it into a productionalized Python pipeline that can basically allow you to build a repeatable process and things like that, that contains your features. So, so I think that's the process of like creating the features that you need to train your model. So the model training, basically, a lot of the time you do it with operators on Kubeflow. So you can use ML operators on Kubeflow to basically train your model. So there are different kinds of operators that you can use. There's TF operators, PyTorch operators, depending on the operators you choose. If you're running on Kubeflow, you have different operators that you can select and you can use for your model training. So the operators, just to go over it real quick, they allow you to like abstract the process of training your model in a production environment. So, or even in your development environment, you basically can have all these operators that basically abstract and help you control the training lifecycle all the way from the beginning to the end and things like that. So the next thing that you try to do once you've done the training, basically working with the ML engineers to do the training, and is to like do the hyperparameter tuning, like what input parameters creates the best model. So because you're gonna have your pipeline train multiple models and you want to select the best performing results. So the data scientists, the ML engineers, the model risk auditors that come into play, they tweak the input hyperparameters and try to see how that affects the output model that get produced. And they score the models and they select the top ranking model. So you can think about it as input hyperparameters are things that variables that are external to the model, things like your learning rates. Basically, they're external to the model, so you basically can control it. You can change the values, and whenever you change the values, it basically affects the model output that you produce. So, you can think about it as a knob, and you're trying to tune it until you get to the right frequency. So you have different combination of input hyperparameters. You basically send them into your model, and you train multiple models based on different combinations of input hyperparameters to see what the results are. So you can look at it this way, like let's say you're trying to train a model and you have different input hyperparameters coming in, parameters that you're trying to optimize the score, and you give it a ranking. And so, you can select the best performing model based on this. So in this case, it's going to be the one with score 94, which is the target goal of your training. So hyperparameter tuning is hard. People do it by hand, but it's very inefficient and error prone. So you need to like have a process of repeating this, and it could be if you're training a lot of model and you have a lot of inputs in that space, the result could be the combination could produce like an exponential amount of models. So you need to be very efficient in terms of how you do your hyperparameter tuning. So there's a project called Katib on Kubeflow. You guys should look at it. It allows you to do your hyperparameter tuning a lot more easily. So basically, you can select a bunch of input. You select your training budget space, and it basically helps you create the tuning and the training that you need. So these are the concepts that you need to like understand if you're looking into Katib. I'm not going to deep dive into it, but if you're interested, you can reach out to me by the side. So you basically create different experiments. You specify the objective, which is the optimization, the optimized results and the metrics, the target variable you're trying to optimize. The search space, which is a possible combination of the input hyperparameters you're trying to use for training. Then the search algorithm, so what the combination of inputs, how you combine them and stuff like that to create your training inputs. So you can use Katib. Like I said, it's a project on Kubeflow. You launch an experiment, you train, and it creates multiple models, and you export your model to like an output location, and you basically score your model and you tag it. So at the end of the multiple training, you can go in and select the best performing model that you have. So this is like an example of a Katib training where you want to select the best performing model. These are like the different input output parameters: accuracy, learning rates, batch size, and the optimizer you excuse me, you selected. So this is the accuracy. You basically have different inputs and different combinations. So at 0.9 accuracy with this and with this, and the optimizer. So you have different combination paths, and each combination path will produce an output. And those output, you now check it to see what the score of the output is and stuff like that. So Katib basically allows you to like combine and select different combination of the input to produce and see which one produces the maximum result output for you. So the other part of it that you work on is the model serving. Once you're done training the model, in this case for the airline data set, so you can use KF serving. There are other serving infrastructure as well. So once you select the best performing model, you can now decide to serve it with Kubeflow using KF serving. So, excuse me. So enterprise ML operationalization goal is, if you want to summarize everything we've talked about, involves the component pipeline development. So the different components that you build. So as a data scientist, you work on your Jupyter notebook. You want to componentize your process, build reusable components, and you work with the data engineers to do this. You can create something called the Kubeflow pipeline, where you compile this pipeline, which basically indicates all the tasks that you want to perform. And you create a process that is repeatable. This is called a pipeline. So this process is basically reproducible, repeatable, and things like that. Then the next thing is to do the hyperparameter tuning, where you create multiple, you change your hyperparameters and you run different versions of the pipeline, and you produce different model output artifacts, and you select the best performing model. Then once you select the best performing model, you monitor the results to make sure the result you're getting is good enough and accurate. Then once you do that, you can select the best performing model and deploy it for serving. So once you do the model serving, you can build an API endpoint on top of it, and you can consume the API endpoints from any of the devices. So that's where you have the smart cars, things like Tesla, you have your phone, you have smart home devices, all connected to this API that you've produced and published. So the goal is to have this process abstracted well enough so that you can reproduce it, you can build reusable components, you can monitor it, and the whole process is automated. So that way you're not spending time, you're not blocked, you have continuous access to data, you're constantly retraining the data, you're constantly producing your model, and you're constantly deploying your model. So that's the whole goal. If there's anything you want to take away from this presentation, it's what we have on this slide, how to understand each stage of this process and how you plug in and what your role is as part of the team providing and deploying ML process in an organization. So I think that's it. We went above time by like a few minutes. Sorry about that. So thank you. And for anyone looking for internship position, we're working on Kubeflow a lot these days. So just feel free to drop emails. Someone will attend to you, and we'll see for those who are interested in working in this space what we can do. Thank you.
Thank you very much, sir, for that insightful session. I've learned a lot, and I'm sure everyone in attendance has too. So we'll be taking some questions, but just before we take some questions from the audience, I would like to point out that the second attendance form will be dropping now, and the secret code is white space. So the second attendance form is dropping right now, and the secret code is white space, all lowercase. Now, to the questions, we have a question from Oseni from the Zoom platform, and he's asking, what's the difference between cloud engineering and DevOps engineering, and which one will come in handy in building a successful career as a machine learning or artificial intelligence engineer? Hello, Mr. Charles.
Yeah, I think they're still the same. I mean, there's a lot of similarities, but each one is good depending on the problem you're solving. So DevOps engineering basically involves the whole process of compiling and operationalizing your workflow for compiling your software and getting it from point A to point B, which is like point A is your input source code. You want to be able to compile, deploy it, productionalize it and stuff like that. So with DevOps, you can either use it on cloud or on-prem, but cloud engineering basically involves provisioning the cloud infrastructure, which is something called infrastructure as a code. So you want to be able to like create a playbook with things like Terraform or Ansible, and there are many more, Chef, Puppet, and use it to like bootstrap your cloud infrastructure. So cloud engineers focus more on things in the cloud, mainly the major cloud providers, AWS, Google Cloud, Azure, and things like that. So that's what most cloud engineers work on. And DevOps is more focused on the CI/CD or the process of deploying things, and it may be in the cloud or it could be on-prem.
Okay, thank you very much, sir. I hope, Useni, that question has been answered. The second question is still from Useni, and he's asking, in this stack, data science, machine learning, and the other subsets of the family related to data, such as data engineering, how good must one's understanding of data structures and algorithms be in order to be able to be good in critical thinking and building problem-solving models? So I think he's asking how related data structures and algorithm is to developing a career in data.
I think it's important, but I mean, like these days, you can unlock all these things by just going online and reading up on them. But the more you do critical thinking, the better you are at system thinking, which is more of what data engineering is all about. So being able to like understand all those things, even if you don't have the background in computer science, is important. So you can go online, check for materials, read up on it, and you should be good to go.
Okay, thank you very much, Mr. Charles. I hope your question has been answered, Useni. And to those of us asking for an access to these slides, we're going to get that from our resource person, and we're going to share that with you. And if you joined in late, don't worry, we have this recorded on YouTube. You can always go back and watch it. I want to say a big thank you to everyone who joined us today. I want to say a big thank you to the interns who were part of this occasion, and we even got a special offer for you interns from Mr. Charles. If you're interested in learning more about Kubeflow, if you're interested in working on that, he has offered an internship to you. You just need to apply to MavenCode. You saw the email, so we'll get that information for you and send and put it up. Thank you very much, Mr. Charles. I'm afraid it's time to call it a day. And like I said, a big thank you to our interns who joined us today. I hope you have gained as much insight as I have. A big thank you to Hamoye team and to everyone who made this possible. Until next time, do have a lovely weekend.